similar. So, okay, good morning, everyone. So today we have Dr. Dai here. I believe most of you already know him. Yeah, he's our new faculty joining us this semester. So he's currently an associate professor in our department. So before joining us, Dr. Dai was an assistant professor at UNC Charlotte, and his research focused on the machine learning and deep learning method to optimize resource management and data access components in heterogeneous large-scale system like the HPC system. So, okay, so let's welcome Dr. Dai to give us the talk.
Thank you for the introduction. Yes, so today's talk I'm gonna talk about the method we use to improve the HPC software infrastructure. Like introduced earlier, we focus on using data-driven method. We call data-driven intelligence method, which I'm gonna cover some of them this talk hopefully. So here's what where I came from. I was actually start from Texas, then go to Oregon for a couple of years, and then go to UNC Charlotte, and eventually landed here. This is my first semester, still getting into everything. So let's just move forward with the content we're talking about. So HPC systems. So HPC systems grows very quickly in the last couple of years. It's considered as one of the major enabler for many scientific applications. Here I show how the HPC system evolves from very early system that so y-axis is the petaflops or gigaflops that achieved by the HPC systems. X-axis is the timeline that system get involved. At the beginning, the system pretty small. I think the Delaware is the first system that almost crossed the petascale scale, almost crossed the gigaflop scale, and the things become much faster ever since then. And every system here shown is the first one in the top 500 list in a couple of years around that time. And the biggest system here right now is in US. It's called Frontier. It's in Oak Ridge National Lab, currently providing just over 1 X flops, which we consider as X flop air, where every system is getting crossed as X flops, and it's very hard to achieve that. Actually, it's been there for a couple of 2 years, I think. We are still looking for the second system that cross that boundary right now. So given the system is getting bigger and bigger, and there are multiple challenges coming across with it. So as the complexity grows, the system complexity also grows. So I show some statistic of the Frontier system. It uses multiple racks. Each rack has 128 AMD nodes, and it's consumed about 400 kilowatts each one. And each AMD node actually have multiple GPUs on it as well. So it's a highly hybrid system, so that I can provide the system you need. I couldn't show the whole system. This is the computation part. The storage part is even more complex in the Frontier system, because we want to achieve the matching storage performance with the computation. So I summarize the complexity into 3 different aspects. The computation complexity, of course, comes from the heterogeneous devices, GPU device, CPU device, and FPGA devices that are currently deployed in these HPC systems. And the second is the storage complexity. The storage complexity comes from the multi-tiered storage system that I widely use today. So this here I show a very high-level abstraction of the storage system looks like in HPC system today. And so here are the computing nodes that are rectangles here, and this is the storage system that people often consider as a storage of HPC system. But today, HPC storage system has been so complicated. It includes multi-tiers of storage layers. On the computing nodes, you have on-demand file system, and multiple of them, they were constructed on demand so that they can be used to serve data access, spiking data access. There are for storage system in between the computation and storage, which was used to kind of staging data in between them. And of course, the traditional part of file system serve as a foundation layer to store multiple data. And those different layers has quite a different way to access them. They work with different interfaces. They have different usabilities. They have different capacities and also the performance as well. You can see the performance range from 2.5 terabytes per second to something like a 20 terabytes per second. So the storage system is also getting so complicated that people have to deal with that today, everything. The last one is application. Application complexity is coming mostly from the machine learning workloads. Machine learning workloads, AI workloads is dominating HPC world today. So I look at the Golden Bell, which is the most prestigious award in HPC world community to really grant these large scale applications dealing with mission critical tasks. In the last couple of years, you can see most of these applications got awarded there are machine learning based, either using deep learning method or using machine learning method to achieve the result we cannot get earlier. So emerging machine learning workloads and hybrid patterns, extreme scales, today, foundational models are getting the application running there more complex. So we're trying to address, as a system researcher in HPC domain, we're trying to address these three aspects together. And my work is basically deal with these three things from a system perspective. So my research is to design and develop the software infrastructure to handle this growing complexity. So this is, again, very high level structure of HPC. You have a very large number of computing nodes, you have a good amount of IO forwarding nodes and a storage node, which are for data access. And those are the very basic structure. And my research is on a computation, how to make computation more efficient, and also on the storage side. The computation part is mostly on scheduling, and also on the storage side, which we're going to focus more on building a robust and efficient storage. So because of the time limit, I'll probably not be able to tell all of them today. At the beginning, I was thinking, let's do this one first, then talk about topic two, which is my typical way of talking about my research. But today, I'm probably going to skip some of them first, and we can talk about topic two first. So let's go first. So topic one, computation scheduling. In this research, my research is mostly to address a very simple scheduling issues. So this is how people use HPC. If you ever have interaction with the HPC system, you as the user log into the login node of the HPC systems, submit jobs or job scripts, such as Slurm jobs. This is some example of Slurm scripts. Those things will be submitted to job scheduling. They will handle all the jobs assignment, resource allocation, job assignment, and who can run first, who can run second, etc. So those things together, they build the foundation of computation. And we did a lot of work here to see how we can efficiently schedule application and computation. I will just quickly go through what we have done, but I'm not gonna get into details here. I'm gonna focus on different things. So this is what we have done. So in this domain, the focus we do is to propose a new, we call it paradigm. It's called data-driven intelligent approach. So before, almost before 2020, before 2017, that was the thing has changed, start to change. Before that time, people do scheduling using different static heuristic methods, such as using traditional scheduling policy, whoever comes first, where can be scheduled, or multi-feature learned scheduling policy. I think we are among the first group doing machine learning-based schedulings, particularly we use reinforced learning. We have a bunch of works along that direction talking about how to use reinforced learning to address scheduling issues. But again, this is not my topic today. Let's quickly see, I can skip to the part I want to talk about. And if we have time, we're gonna come back to this part. I've been talking about this part too many times. Let me, oh, okay. That'll be a lot of skip. See, it's the best way to do that. I'll just skip a lot of these slides. Sorry about that. If I get time, we can come back later. But I want to talk about something more interesting. The second topic, storage. storage on the robust efficient storage system. So on this one, I think we have done a lot of work in the last couple of years, storage side. So here I show the similar roadmap here, but I want to talk something we are doing right now. I think it's interesting to share. So we work on two different things. One is to improve the efficiency of the HPC storage systems. Here we mostly focus on building storage, new storage file system so that you can get the data access much faster. So we start from proposing the first graph-based storage system, and we actually implement it in multiple different ways, in-memory ones and also on persistent memory ones. Another theme of this research is on robustness. We start with checking file system issues. When you have a file system, you store data on it. As things run at a so large scale, data may be broken as it runs. So how to check that data broken, how to fix it is what we have done in robustness part. Again, we have done a lot of work here as well. But those are, you already talk as well, but I want to talk something today is what we're doing right now. It's called intelligent understanding IO logs. Why are we doing IO logs? Because those are the converged topic of these two things. On the robustness part, we focus on understanding the logs of the file system. If the application runs on your file system, it creates logs to represent what is going on for the application. We spend a lot of efforts trying to understand how these logs represents, if this log represents some issues in the file system, and if we can fix them. And the efficiency part, we care a lot about the performance. We want to check the IO logs as well, but not in a very detailed way. We use the logs as assistant to help us identify if there are performance issues. So now, since we have done both of them, we're trying to do right now is trying to see if we can give a log file of the application, if we can identify any performance issue of the application, the performance issue particularly on the IO side. So we can work on both sides, so robustness and efficiency as well. So this is the work we just published in the summer. It's called ION. This is a collaborative work done by us and Charlotte, UNC Charlotte, my previous students was there, and also Berkeley Lab, Ohio State University as well. So the ION idea is to use language model as a tool to understand how the IO logs created by applications can reflect the application performance, and hence to improve its performance by providing recommendation to the users. So let me give you some background what is this all about. So high levelly, if you look at the HPC IO stack, you're looking at the right figure, which I just mentioned briefly on the hardware aspects earlier, but this is the software aspects. Again, it's similarly complex, right? As the top, the application start to access data until it reaches to the very low level storage hardwares. It goes through multiple layers. In the beginning, it goes through some high level IO libraries, such as using HDF5, necessitating, reduce this data access layer, then turn those data access APIs into lower level APIs, such as MPIO, POSIX, STDIO, standard IO requests. Those requests will go into IO forwarding layers, depends on what system was deployed there, and then finally arrive at a part of file system, even to the storage systems. So those many layers, every single layer of them matters to your performance. So if it's never like if I use HDF5, my performance is gonna be just magic. It's something HDF people promised, and that's something we cannot deliver as a storage community as a whole, just because of complexity. So there are so many layers there, and every layer has multiple configurations, multiple way of using these layers. It's very, very hard today for a domain scientist. If you're a scientist, you're trying to write application in the HPC scale, and very quickly you notice that computation is no longer your bottleneck. Most of the time, your bottleneck turns into storage, data access. And when you get into that situation, what you look at is this stack. And what you want to do is to see,
oh, my application is not doing well here. How can I make it perform good? So it's very challenging for them to do so. So what they are doing right now at NERSC, for example, one of the largest open community HPC center, most of the people working at NERSC, domain scientists, have to rely on IO experts, like while they collaborate with here, at least here, rely on them. So if you have IO issues, they will basically submit a ticket, and those tickets are going to route through ticketing system, get into their desk, and they start working on it by looking at the application, looking at the trace. The trace is one of the most important thing here. So they will work on it. So application developers often do not have the proper expertise to do that thing. So the wrong behavior of the IO, including multiple issues. We can show here improper use of product IO middleware, IO request misalignment, inefficient read-write patterns, share files between ranks, and load imbalance of our ranks, load balance among storage servers. Those are all possible issues. And the performance impact, we just show example here. E2E is a domain decomposition kernel, which is widely used in many scientific applications. We saw this is reported in our study as well, that the load imbalance issue in the original code of E2E leads to 10 times worse performance than that's the original E2E code. After we fix it, we get 10 times better performance just by changing that single thing of IO imbalance. We'll see some of this example, I think, hopefully later. So what people are doing right now to address these big issues, because IO is just so complicated, nobody can figure out how to use it. And it is also impact the application performance so much. So what people are doing now is 3 layers of operations. So first, we try to use some profiling tool. Here we list Darshan and Recorder, which are 2 open source ones, are very popular ones. We use this profiling tool to, while the application is running, we use the profiling tool to profile what is going on from the application, majority on the IO operations. So with that, we will start using some analysis tools here, list here, called PyDarshan, Explorer. Those are developed by Berkeley Lab as well, to analyze the trace, to see, for example, to visualize the trace, to see how it looks like, and also to eventually, hopefully, with a proper background, you can get an idea of what is going wrong. And also there's a tool called Drishti, which is also developed by our collaborators to diagnose the issues, potential issues of that trace. So essentially you have 3 ways of doing so, right? You have to collect the trace, you have to open the trace, look at what's going on in the trace. You probably need to visualize it, probably need some data analysis tools to analyze it. You probably use Drishti to understand what's going on here. So that's what the current solution is. But all these things require a domain expert. So this is the beginning. This is what the analysis tool looks like. As a user, you do application, you have IO, and that IO operation was tracked by Darshan. This is a log, looks like. I think I have a better view later, but those are the logs. It's basically a bunch of operations done by the system. Those logs can be done, analyzed by Darshan or other visualization tools. And this thing gonna be shown to the user. A user need to figure out what's going on. So as a user, when you see something like this, it's actually not very easy to understand what's going on. You have to be equipped with the proper knowledge, which understanding, for example, when I send IO to the storage server, what is going on, where the buffer is, how the concurrency was achieved, why these storage servers are all serving this IO, why they are not. You have to have this background knowledge. And turn this analysis into actionable insight require a lot of domain knowledge, and that is not something domain scientists would like to learn normally. And a few experts are available to do that as well. So in a NERSC center, in data centers, big HPC centers, it's very often that you have to wait for a month to get an application IO issue addressed, because just not so many people are working on that domain. Another tool we mentioned here is called Drishti, that was developed to kind of help this scenario where the IO operations And then the trace file created by the user will go through some analytic processes and provide some descriptive insight. Drishti is a tool that essentially take the input of the document and try to give some very high level recommendations. This is what Drishti could provide you when you give the tool a trace file. Here it basically says, the red one shows some issues. It says application doing a lot of misaligned file requests. So recommendation is you should maybe try to fix it. How to fix it? Those are basically predefined recommendations. So Drishti tools are hard-coded by checking the counters in these log files. If there's a counter there, will trigger the corresponding issues. So I will report that issue and also give suggestions. It's a similar thing here. So the Drishti was done in a trigger-based way. So all the threshold setting will be done by the programmer of Drishti, not the programmer of the application. So Drishti programmer has to think of a bunch of triggers that whenever I saw this number, I would just trigger some issues. That's one thing. So those are clearly not specific to this particular application. These are not specific to any system. These are very generic. So which limit Drishti usage a lot. So Drishti currently is only used in one center and it cannot be extended to others because basically they're only working in that one center. So it also have very generic output. So it does have static code examples we showed earlier, and it does not give a good explanation of what's going on in the system. And it ignores many factors that are overlapped. I'll give some better example later about those issues. But Drishti, again, as a very helpful tool here because it simplifies what a user need to learn about their trace. It simplifies that a lot, but it still has a lot of issues here. So that's where the language model part came from. So when we work on with them on this project, and we see the issue of Drishti, and we're thinking about how to address it, the very first option at the moment came to us is why don't we use language model to see if we can, because those log files are basically human readable text. And if we can use language model capability to learn what is going on in these log files, and maybe language model is able to understand it, maybe it can give us some good understanding. So, and it's nice because domain scientists can easily interact with language model. So we can ask questions. It doesn't tell you crazy things like crazy triggers or crazy numbers. It just keep telling you something you can understand. So we saw language model as a potential options, and we do try that. So we try that. We try to see if a easy prompt like this, plus a real world trace. This is a trace from AMREX running in the scale in the nurse center. And this is how the trace file looks like. As you can see, those are text files basically. It's understandable by human and as well as by language model. We use a very simple prompt. We asked ChatGPT-4 at that moment. That was about a year ago. So that's what ChatGPT is still available. We asked ChatGPT how you can, if you can do something about it, right? That's the beginning. And this is what it replies. So we asked that, okay, you give this trace file, could you help me decide if there are any error issues in that trace file? If yes, could you do something about it? Like give me why, tell me why, and give me some suggestions. And this is what ChatGPT tells us. ChatGPT says, okay, if you want to do that, you can do that in these steps. Step 1, step 2, step 3. And if you can read those things, those are typical ChatGPT outputs, right? So there are a lot of things, but it's just meaningless. It says, if you want to do that, you can first check open and close time. You want to do that, you can first check the volume and set operations, and you can do, etc. I mean, this is a summary. Summary says from the log, there's blah, blah, blah. And to proceed with the deeper analysis, it would be great to plot the time. It would be great to do something else. So the output of ChatGPT 4.0 is pretty bad at the moment. I think it performed really bad because it pretty much says that you should talk to an IO expert, not me, right? He says that. But we do see some good things here. We do see some good things here because it looks like it understands. It understands the logs because we don't provide much information about the logs. We just tell, here's the log. They are from Darshan. So I guess their training data included that part. So they know what Darshan is and they know how to interpret that data, which is great. And we do try that same thing on 4.0. This is after the paper was published. That was 4.0 came after that. And we do try that on 4.0. 4.0 actually gives something much better. So this is how 4.0 looks like. The same thing, the exact same prompt, same file, same request. 4.0 this time, not asking you to get help from others. It just tells you, this is what I do. I first do an overview, and then I do each of the different types of IO activities. For example, it cares about POSIX read and write. It cares about data access patterns. It does even more than that. It does right size distributions. It does alignment check. It does variations in our performance across banks. Sometimes when I look at this result, I kind of feel they must train their new system using our results because this is what we report in the paper. And this is clearly something similar to what they can do today. So they basically list the potential issues and recommendations. For example, here list 3 issues of the application, which actually is pretty close. The issue itself is pretty close and pretty awesome, to be honest. But if we look at the details, this is the issue of most language model-based tools, right? If you look at the details, it starts to have problems. Overall, all good. Look at the detail, it's not. So for example, here it says, oh, you know what? This is the file you access in the application. It does this and that, and they have a lot of analysis based on that. However, that is just one of the 11 files this application uses. So it ignores the rest, just pause one and start to have a lot of recommendation based on that one. So apparently it could be wrong because others might be important. The second one is this only talk about the POSIX read-write. And POSIX is known that to be the least efficient way of talking with storage server in the HPC scale. In HPC applications, you use MPIO, right? You use MPIO at minimum. You use MPIO with some advanced features, MPIO with collective IO, MPIO with asynchronous IO to improve your performance. But this application do use MPIO. It does use MPIO, but nothing was reported at all. Apparently, I guess GPT-4o doesn't really know much about that part. MPIO is important. And it does do the variation of performance across ranks, but it didn't mention anything about if you do IO across, if the IO is efficiently across different storage servers. It basically focuses on one part of the imbalance. Again, storage server balance is not discussed. So this is summary. So first one, if we look at this new result, you have to admit first that GPT-4o is much better compared with 4, which I think is one of the reasons the present as a useful to help people. So it is much better. It has the same level understanding of the complex documents and be able to figure out things, but it still has the similar issues. Kind of stop them from being a practical tool. One is they provide inaccurate information. Many times they have to say it missed important aspects of the IO stack. They just talk about one thing because they don't know another thing is more important. And it lacks of domain knowledge. So for example, what is a good utilization of power file system? They don't have that knowledge. They will just say something very high level. Say, okay, if I do a lot of small IO, it's not good. Everyone knows that, right? Everyone knows that if you do small IO, it's not good. But the problem is what kind of small IO is not good? And what scale is not good? Those kind of stuff, they don't have the ability to do the reasoning. And they don't have the domain knowledge to do so as well. And they create hallucinations. But hallucinations here, in 4.0, we have to admit from our experiment, we saw it has been depressed a lot. So we really don't see much of wrong, just out of nowhere claim in the response. But still, there are some. For example, I think this one is not clear, but we do have some other examples where they just falsely claim that if the application is doing right size between this size to this size, then it will be all correct. It will be all optimal. That's a hallucination because that time range, that set range is normal. It's very popular by real world applications. But people know those are not optimal because there's always a distance between what people use it and how we like people to use it. So as a storage people, we know this is not optimal, but people still use it because it's convenient. But they will think that is optimal, even there's no people tell optimal. They just saw this a lot. They just saw this a lot in their training data. They consider that's optimal. That's a problem, and we saw a lot from their GPT response. They lack references. They don't tell you why. Just tell you, okay, this is, for example, SMILE is an issue. They don't tell you why SMILE is an issue, and they don't have reference for that, which clearly is not the ideal scenario we real practical usage. And accurate recommendations are highly, it's very high level. And I think if you really want to deploy those things or change your code, you have to rely on our experts to do that, which in my opinion is not a.
Yeah, I mean, you can finish your last one, but yeah, I have some question
Go
about,
ahead.
for example, for the last two, what if you continue asking, where is the references, right? Maybe they will give out some references, probably error notes, but I don't know. And also unclear recommendations, very high level. You can ask them to explain.
Yeah, that's right. We did try. So
Okay.
we torture them a lot. So we do keep asking questions, and very quickly after 2-3 rounds, they start to make up things. This is a problem we still observed. So if you stop here, it's all right. So most of the content actually came from the trace we provide, and this is actually even not so wrong. It's okay, but if you ask that 3 more rounds, they will start to make up things. And for example, you can see, oh, you said there is a non-aligned IO issues, but is that a real non-aligned issues? You just ask that, is that a real non-alignment issues? He will say, yes, you are correct, it's not. And start to make up things
You
about
help
that.
them to. And also about these 3 recommendations, I wonder from your experience, are they ranked or they should be treated equally?
This is not ranking at all. I think they shouldn't be treated equally as well. But I don't think it's possible for them to understand. which
Yeah,
one
I
is-
think it would be good to, ChatGPT recommend this, but like maybe explain the confidence of this recommendation, like the uncertainty quantification. And also, I have another question about the GPT-4o. Since you mentioned that, I wonder, because I'm not familiar with ChatGPT-4o or something. I wonder, I just checked that the improvement that is that it can integrating multimodality data. So I wonder, when you compare these 4 and 4o performances, whether it's because it enlarged the training data or it's because of the improvement is because of the model. So I'm not sure because it kind of, for me, is an unfair comparison. Is that when you ask a ChatGPT-4o, it seems like you also hinted that probably this time they incorporate a larger training data set.
Oh, in the problem we ask them, they don't. We don't.
Yeah, but you think because
We think they are. Yeah, we think so that's a good question. I think our guess is that Fall is able to do more. I would say it actually follow your instruction better than the GPT-4, because GPT-4, you ask the same thing. You ask the GPT-4 to list IO issues. Well, GPT-4 doesn't do that. It just lists the steps you should do to identify IO issues. But 4o actually apparently follow the instruction much better. It actually do exactly what you want. It lists all the IO issues. Although whether it came from their increased the capability of following, or doing reasoning or following the human behavior, or it's because of more training data that, that's something I really don't know.
Yeah, so I
guess
think
it's the,
one key, I mean, for me, a fair comparison is that when you publish your paper, ChatGPT-4 has already trained on your data already. Otherwise, I feel it's not I mean,
yeah,
it's a good task, but I feel it's a little bit unfair in my
4 and
point.
4 comparison is not fair, right? Because you don't know if 4 take our data or not.
Yes,
That's true.
yeah, that's my guess. So was your paper published after,
Before 4.
before 4.0, but after 4?
After 4.
So I wonder if 4.0 read your paper or not. So I think that's the only,
We don't know. The problem is we don't know. So
Yeah.
I think they do. So we show something what our first paper looks like, and then you can see it's probably closer to what a fall does. We'll see that later. So we remember when we do this study, fall is not there yet. So what we saw at the beginning is something like this. Oh, sorry, something like this, which makes this basically not useful at all for any domain scientist. If you ask that the system, okay, this is my application log, tell me what should I do? The application that GPT-4 tells you this, and it's just not useful. It's not useful at all. So when we start working on these problems, our first initial idea is to increase the ability, of GPT-4 with the 2 goals, right? First of all, we want to provide some robust detailed knowledge about the HPC system to the language model. And I also want to make sure that it does not have so many hallucination created in the middle. So we do very simple things at the moment. Doing context learning, we provide, we call it the word knowledge about HPC systems, especially HPC storage systems, like how I.O. is going through the system from application to storage server. Basically I would say a high school, but not high school, a graduate school 101 kind of course to the language model, how I.O. HPC I.O. works. And we also provide these prompts to force the the ChatGPT think from step by step. So we do that 2 things, very simple prompt engineering stuff actually. And this is how it looks like overall, but it's kind of looks complicated, but it does very simple things. Parse the log claims, we do a parse. The parse helps to isolate each different layers so that it never miss a layer. So all these layers will be prompted to the language model with the word knowledge and also in context learning content, as well as the chain of thought ideas. And we create a bunch of outputs and we kind of summarize them together to the users. And it's pretty simple strategy. And the solution, we have a tool online put there, and this is how it looks like as output for the same workload on our system. Again, this is before 4.0 came. And you can see what it provides is more like what 4.0 has. It does not tells you you should try something, just list of I/O issues and why they think this is issues. And for example, small I/O, it says the frequency of small requests 99.94 being smaller than RPC size suggests a potential application issues. So things like this. So this is what we kind of get before 4.0 came. And it's able to capture different layers of I/O operations, able to tell the shared file I/O, which is the imbalance issues across on the storage server. So 2 things are captured here. So we saw this today. If you look back at what we do, and we feel it's basically on par with ChatGPT-4 can do. Well, GPT-4 is free, and we are also free, but GPT-4 is available for everyone. So it's not that interesting anymore for us. But it's lucky that we published before that. So today is like, I think many research is doing this way. You have to be faster than them, OpenAI. Otherwise, they get a new system and your work was part of their system already. So But still, many issues exist. It's not ready to be used for domain scientists. We talk with them, we talk with nurse people, they still feel this is not good enough. I think most important part is here. So we think they are not having enough domain knowledge yet. Even so, even today, for all, I don't think they have enough domain knowledge about what is good, what is bad. They still largely based on, they may read some papers in their training data, they may read some some blogs on their training data, but they don't exactly understand what's going on. They also hallucination issues, like I told you earlier, that consider popular opinion as golden rules. This is something they do always do the wrong thing. And they don't have reference, they don't provide why certain behavior are problematic. And by reference, we mean something serious, right? Something from paper, something from a serious study, evaluation study. And also has academic recommendation, it's still the same thing. We also have the issues. We do not give good recommendation according to each simple issues. So what we are doing right now is we call Ion Pro. Ion Pro is the next step. And we don't have the, I don't have the slides here yet, but I can quickly show what output looks like for Ion 2. Okay. Oh, it's not shared. 1 second. So this is what Ion 2 output looks like. So still working in progress. I don't know if I have to make it larger. This is HTML format. We try to address several issues. One is we try to make sure the most important thing we provide here is to provide reference on the issues. So every single issues we described here will come with a reference why people think this is good or bad. Most references are paper or technical report that people published last 10 years. And we also try to provide the recommendation just right after the description of the issues. For example, you have the issue that says, okay, there's a small write issues. 67% of the reads are small write 1 kilobytes, and we see that the evidence is why. We think that's a problem. This is an evidence that this is recommendation. Recommendation came from certain papers. We still have some small bugs here, duplicated references. That's part of the rec system issue. So what we do here, we do 2 things. One is we use rec. We create the knowledge. We put a domain knowledge into a rec database. So everything was handled pre-processed there. So in this case, the GPT model knows the additional domain knowledge about what is going on in the system. So for example, if we say small IO is an issue, then we have to refer back to the paper that actually says that what kind of small IO is an issue. Then we use that as reference to determine if the current thing is wrong or right. That's one thing. A second thing, we do self-reflection. So we enhance the whole diagnosis step into multiple step workflow. In the middle of each steps, we do self-reflection. We ask the model to reflect what it generated and making sense or not. So this self-reflection can remove a lot of hallucination, because if you consider something is right, for example, the small right issue, if you think this size is golden size, is optimal, and then you weigh the context, because the size, the right size context also says a lot about that, right? If you have the right size 100 kilobytes, for example, 100 kilobytes to 500 kilobytes is a golden right size. When that pop up in the diagnosis, it also goes with all the context from the rec database. Altogether, we'll go through a reflection phase. Reflection phase will tell, oh, you know what, the paper you cited here is not supporting this is optimal. This is just supporting this is popular. It's not optimal. So we will actually delete that diagnosis. So we are able to achieve much better accuracy. Currently, we have built up about 50 to 60 use cases, and these use cases are from real applications, and there are error traces. There are error traces and also our diagnosis. So we have the traces, our diagnosis, And we share them as, and also the ground truth, we share of them as the a new data set we are offering that to the community so they can do a better way to diagnose issues. So I couldn't tell more about the detail here. I hope I can. But I think we are just the beginning. We're just beginning. We're just beginning at using this kind of tool to address a performance issue of applications. We all know that GPT is very good at programming, very good at writing your code for your homework assignment. But I think the issue with GPT is it couldn't tell you, it couldn't create a good performance code. The code it provides does not consider much about the performance, especially for domain-specific problems. To identify for like I/O, right? If you ask them to do I/O operations, they don't consider, should I use MPIO or should I use POSIX I/O or should I use collective I/O? Or if I use POSIX I/O, what should be the correct, let's say aggregators? What should be the correct size of the file so that I can do to take advantage of the full bandwidth? These are not something GPT can do. This is something I believe similar technology can help in the future. Like I said, it's the beginning, we're trying to push forward this in the future. That's actually the major part of the talk. I want to take back, oh, this is still here. You shared the other screen. Yeah, I shared the wrong one. Okay, so this is a major part of the talk. I have another set of talk about using reinforcement learning to do some job scheduling optimization. I'll just skip that. I think that's it. So have some time to ask questions. Interesting.
Okay, so any question? Okay.
Oh, so this is actually like a very naive question at the high level, right? So, I mean, I have very high level familiarity with the application, right? So like you said, a domain user, like somebody comes in with HPC application, right? And then because they don't understand the nitty gritty of this I/O operation, they just cannot handle the whole scenario, right? Now, the goal is that give them like don't wait 1 month for the solution to come to you. Here are what you can do, right?
Yes.
But wouldn't it be better? I don't know whether it is doable or not, but wouldn't it be better that like, I mean, don't give this end user too much flexibility. Just kind of tell me what you need, and then I'm gonna optimize it myself as a HPC system, right? Because if even I will give you instruction, you're gonna screw it up probably, right? So because you don't know what's going on, right? So this is probably ignoring a lot of the cool things you're doing, yes. But like at the high level, like is that also relevant?
Yes. So that's actually that's a dream. That's a dream of us. we dreaming that for many years as HPC storage people. And the problem with that is it's like a compromise. Today, we can still provide you like HDF5. HDF5 is a higher level of library. If you work with any chemical application, you probably use it already. So it provides you some very good foundational, good performance. It's like if the storage system is able to offer you 100 gigabytes per second, that probably can guarantee you 50% of it. So no matter how you deal with the application, they can do some kind of optimization. But that rest 50% is not they can do. It just cannot do it. So it's complicated to a level that I have to understand what the application is doing. So it's like application is doing what, but our layer doesn't know right now. You're calling me, but I don't know what you're doing. So if you want to get the last 50%, I have to know exactly what you're doing. And I assure you, we are all try our best to do that, but we couldn't. We just couldn't. So right now, at least, we couldn't. Just because let me give you an example here. So for example, your application is doing a bunch of, the application is writing to okay, let's do this. Like, you're running a big application. You do very typical operation, like a checksum. Not checksum, checkpointing. You do checkpointing every couple hours because your application runs for a month. You don't want to lose anything. So you checkpoint every couple hours. So what is the best way to do checkpointing? Really depends on, at that moment, what is the size of data, how the data was organized in the memory, and how you want to write that to the OST. So it's highly dependent on that. So using the same, for example, I use HDF5 to do checkpointing. It has a high level API, I can call that API. But that API will do that it might fit one of the scenario. It might fit very well for, if your size is moderately big and you're doing this many bandwidths to this many OST, that works well. But as long as your application doesn't do that, it will just drop like this. So we very often see application performance goes from 900 gigabyte per second to 100 or even to 20 gigabyte per second. That's what we saw every day. And we're trying, but it's not there yet. So that's why we want people and the domain scientists want to know this. For example, last week I ran my application, it's 900. This week I run it, it's 10.
Right.
I need to know why. And that's what they're always asking. So this tool is that you can just use it. You get your trace. So upload your trace to the tool tells you what's going on.
Right.
Why it's not working this time. That's what that's question.
Very enough.
Okay, I also have one quick question. So I believe we should have this log file, right? So why you don't train a small language model like use a BERT or some other model and then to see how about this performance? Because I think all the patterns looks like they have a regular pattern. I don't think it's will be very complicated task. So you just use the like you have the ground truth data, just train a small language model. I think it can be easily to beat the ChatGPT because ChatGPT they don't have this kind of training data.
Yes. So you talk about fine tuning, language model to do that.
Probably you can just train a small language model.
We actually do both. So we're not using language model that work. So what we do is we use traditional machine learning model and we collect the L requests and their performance. We collect a lot of them and we use machine learning to try to predict when this happens, what's the performance might look like and how we can. The problem with that is you cannot improve it, right? You cannot. I saw the pattern of the L pattern. I know it's gonna be bad, but I cannot push that back to, what is the problem? What creates that L pattern? I don't know what creates that L pattern. The application do something and I only get the pattern. So the best way to do that is I get the pattern and I also get the application and I understand the application, understand what it's doing, what is going on in the runtime. That is the hard part. So you just cannot push back to that part. If I have only the trace, so right now what we can do is we can do two things. We can do, when you run application, I can real time predict. I can do that in real time. We can predict if the application gonna go well or bad. That's it. But we cannot tell you, you should change something to make it work better. We just cannot tell that.
Okay, I see. Thank you. So any other question? No question? Okay, so if no question, let's thanks on the back.